Okay, in this video I'm going to do a couple of example problems from the presentation slides on frequency hopped spread spectrum. And so this is the topic, frequency hopped spread spectrum. And here is a summary of the equations that we're going to use in describing what's going on here. The basic idea is that what we're going to do is, instead of just transmitting at one frequency, we're going to transmit at a variety of frequencies and hop around amongst those frequencies. So for example, here is a set of frequencies. Okay, so this vertical axis is the frequency axis, and we have the frequencies divided up into multiple channels. Okay, and so, for example, in Bluetooth, we have 1 megahertz wide channels, and we've got 79 of them. In any case, what we do is we transmit at one frequency for some period of time, then we hop to another frequency and transmit at that frequency, then to a third and a fourth, etc. And what we do is our transmitter and our receiver hop together, and that allows us to send information over a wider frequency band, which is resistant to adversarial jamming and also adversarial interception. Resistant to jamming because it's tough to jam a wide frequency range all at once, and resistant to adversarial interception because our adversary doesn't know the sequence of hops that we're going to take, whereas our receiver does. Okay, so that's the idea here. And so the idea is that we're going to, as shown here, as a function of time, we're going to hop, and so we have frequency versus time here, and we're going to hop from one frequency to the other, and we're going to stay at each frequency for some certain amount of time. Okay, and what we're going to do then is, this slide just says that the transmitter and the receiver are going to stay in sync with each other based on having a shared pseudorandom number generator. Here's some equations that help us keep track of what's going on. Basically, we have now a hop rate, where how many hops per second. The inverse of that is the hop period. We also now have the pseudorandom chips, or each chip is a 0 or a 1, and these chips are what are used to determine the hop frequency number. Okay, and so if we have the number of frequencies in our channel plan is LC, and if LC happens to be a power of 2, then it takes M chips per hop. So this is a familiar sort of relation between L and M that we have in these situations. And so, for example, if we're using 3 chips per hop, then we can create hops amongst the channel plan of 8 frequencies, because 2 to the third is 8. So if we have 8 frequencies in our channel plan and we want to hop among 8 frequencies, we need 3 chips, or random bits. A chip is another word for a random bit off of that pseudorandom number generator, to create that hop sequence. And so we have a relationship between the chip rate, the chip period, and the hop period. We also have a very similar relationship between the chip rate and the hop rate. They are related by the constant m. Okay, and so these are the most basic equations that you can use to characterize what's actually going on. And so here's an example where we have a channel plan with 16 channels in it, and we have a time axis here, and you can see that we're hopping from channel 12 to channel 3 to channel 11, channel 15, channel 13, etc. Okay, And in practice, what we do then is we let our pseudo-random number generator generate these chips, which are random bits, essentially, and we use them to determine the next frequency hop. And we use a lookup table to do that. And in this problem, this example problem, what I do is I give you the chips and the hop sequence and ask you to determine, fill in the table. Okay, so let me fill in this table for you. And what I'm going to do is I'm going to say, there are 16 channels, and so it requires 4 chips per hop to determine the next channel. Okay, and so I'm going to divide these chips up into groups of 4, like this. If I can do it. 0, 1, 1, 0. So I'm going to divide it up into groups of 4, and then I'm going to count them to make sure I really do have the right number of chips here. And it looks like I do. Each 4 chips corresponds exactly to 1 hop here on my chart. Okay? And so now what it's simple now. What I can do is I can say, okay, if these 4 chips, 1110, gave us frequency F12, then that's what I fill in here. If 0011 gives me frequency F3, then I fill in 0011 in frequency F3. And so on. Frequency F11 is 1111. Frequency F15 is 0101. And we certainly hope that the one-to-one correspondence here holds. The next one, frequency 13 is 0110. And so on. You're just reading these things off one at a time. So 7 is 1001. The next one is 10. It's 1101. The next one is frequency F6, which is 1011. I don't think I'm making a mistake here. F6. Next one is F1, which is 0000. Okay, nice. Next is F9, which is 1100. Next is F2, which is 0001. And finally, we have F16, which is 0100. Okay. And let's see here. We don't have any F4s in our diagram. And so that one's still blank. We don't have any F5s either. And we don't have any F8s apparently, right? And we don't have any F14s apparently here. And so what we're going to do is we're going to try to fill this in to see if we can fill them in a way that makes some sense. And let's see, which binary numbers are we missing? Let's spell them out here. 0010, 0011, 0100, and I'm going to see if I can figure out which ones are missing. Just enough. Okay, so 0000 is accounted for, 0001 is accounted for, 0011 is accounted for, 1011 is accounted for, 1001 is accounted for, 1100 is here, 1101 is here, 1111 is here, 1110 is here, 0110, 0110, where am I here? There it is. 0101, yes, and 0100. Okay, so here are the 4 that are missing. And I did sort of an exhaustive search there, but we're missing 4 of them over here, and here are the 4 that we're missing. And we're interested in gray coding these, and to gray code these, we want there to be at most 1 out of the 4 bits changing every time we move, like this. And you can see that this is gray coded so far. Gray coded we talked about earlier. This is in fact gray coded so far. So let's see what we can do to fit in here. 0110, what would fit in there to gray code between these 2 values? The 0 and the 1 are apparently staying the same, and I guess a 1 1 or a 0 0 would fit here. 0 1 1 1 is in the list of unused ones, so that has to be it. Okay, so now we've used that one. And you can see now that this is gray coded. Only the 4th bit changes, and then only the 3rd bit changes. Now let's go up here and see what we can fit in this spot. And it looks like we have the 1 and the 0 here are fixed. And so it would be either 1101. Is 1101? No. The only that we have that start with a 1 or a 1 0. And so it's 1000. Okay. That's the one that has to go here, and now we're gray coded here. We change the 4th bit, then we change the 2nd bit, or chip. Finally, we have these 2 guys that have to go in these 2 spots, and if we put this one next, that would work. Can we put this one here? No, that would be 2 changes, so 0010 must go here. And what looks like a 1010 must go there. And now we can see that these guys are also gray coded. Change in the 4th bit, change in the 1st bit, change in the 4th bit. Okay, so this is the example that I did on the board. And so we have taken the values that were given in the table, and then we were able to fill in the other 4 values based on demanding that we have a gray code here. Okay, so I hope this video helps on this. Thanks for listening.